In this screencast, we're going to look at building molecules from elements. So we're going to look at the 5 most common elements that we'll see in Organic Chemistry 1. First, we'll look at the electron configurations. Then we'll make Lewis dot structures. And we'll convert them to dash formulas. We'll look at the meaning of a condensed formula. We'll also name them and then look at some functional group properties of these molecules. So let's start off with writing down what these elements are. We're going to start with hydrogen. Next, we're going to do carbon, nitrogen, oxygen, and fluorine. Let's first go ahead and look at the electron configurations. So hydrogen has 1 electron, so it populates the 1s orbital, so there's 1 electron. Carbon is atomic element 6, so it has 6 electrons, fills the 1s, there's 2 of those. Next is the 2s, there's 2 of those. And then we move into the 2p, so there's 2 of those. Nitrogen follows, adding 1 more. One S2, 2s2, 2p3. Oxygen adds 1 more. And then finally the halogens, specifically fluorine, has 1s2, 2s2, 2p5. So let's go ahead and draw in the valence electrons for each of these elements. So for hydrogen, there's only a single valence electron, so we're going to represent that as a dot. For carbon, we're specifically looking at 2s2, 2p2, so there's 4 valence electrons. So we're going to add them around the carbon such that we're not pairing them at this point. Let's go ahead and do the same for nitrogen. So now we see 2s2, 2p3, that's a total of 5. We add them in first by not pairing them. Then the 5th one, we're going to go ahead and pair. So that means nitrogen has a single lone pair in its normal valency. Oxygen is 2s2, 2p4, so there's 6 valence electrons. We add those in unpaired. Now the remaining 2, we go ahead and pair. So that means oxygen in its normal valency has 2 lone pairs. Finally, for fluorine and halogens in general, there's 7 valence electrons. We add those in. We then pair them up. And we can see that halogens have 3 lone pairs. So what you see moving from carbon to nitrogen, we can go ahead and make a table here to summarize our results. Let's just say number of lone pairs in the normal valency. Hydrogen has 0, carbon has 0, nitrogen has 1, oxygen 2, fluorine 3. So let's from now go ahead and we're going to make a matrix where we bond this row of elements first with hydrogen. So I'm going to draw that in blue so that we can see what the nature of a chemical bond is. So we're going to take this hydrogen atom and then bond it with each of those elements to fill up the remaining valencies. So if we do that, we have hydrogen bonded to hydrogen. So we pair up those electrons. That then makes a bond. So 2 electrons make a bond. In this case, that is a single or sigma bond. So another way that we can represent a bond is with a line. So that's another representation. The two dots become a line. That's a sigma bond. We can go ahead and do our carbon now. So we see that carbon has 4 unpaired electrons. Now we're going to draw in 4 hydrogen atoms to complete those bonds. So what's another way to represent that? Again, using the dash formula, where the lone pair or the bonding pair is replaced with a line. So that's a little bit easier to interpret in some sense. You just have to recognize that the line means 2 electrons. Moving to nitrogen, it has a lone pair and then 3 unpaired electrons. So each of those will pair up with a hydrogen atom. And if we draw the dash formula, there's the lone pair, there's the 3 sigma bonds, and here are the 3 hydrogens. Our next element, oxygen, 2 lone pairs, unpaired electron, there's 2 of them. We bond those to hydrogen, then we can convert that into this type of conventional drawing. So that's water. And then finally, for fluorine, we see that we're going to form a single bond because of the 3 lone pairs. So now we can capture another piece of information. And again, this is based on the normal valency. So over here in red, I'm going to write number of sigma bonds. And we'll generalize this later when we look specifically at the molecular shape, including hybridization. So hydrogen will always form 1 bond. Carbon, if we count them, 1, 2, 3, 4. Nitrogen 3, oxygen 2, halogens 1. So compare that with the number of lone pairs above. So carbon starts at 4, it has 0 lone pairs. Nitrogen has 3 bonds, 1 lone pair. Oxygen 2 bonds, 2 lone pairs. Halogens 1 bond, 3 lone pairs. So these are elements that are in their normal or neutral valency. There's no charge. If the element does not have this number of bonds and lone pairs, then it's going to have a plus or minus charge, which we will use an equation to determine that. Before we do that, let's look at, so what we're going to do now is look at another convention for representing these molecular structures. And so this is called the condensed formula. So in the condensed formula, you're basically writing the elements in a line like you would a sentence and using a subscript denoting how many of each type there are. So for hydrogen, we have H. The next molecule is methane. That's CH4. We have ammonia next. That's NH3. we have water, that's H2O. And then finally we have HF. Hydrogen fluoride. Next, we're going to go ahead and calculate the molecular weight of each of those. And basically, we're taking the atomic weight times the number each time occurs in that formula. So for hydrogen, it's equal to 1, so 1 times 2, we get 2 grams per mole. Methane, carbon is 12, so 12 plus 4 is 16. So we'll write that over here, grams per mole. Ammonia, nitrogen's 14, plus 3, that's 17. Water, oxygen is 16, plus 2, so that's 18. HF, fluorine is 19 plus 1, so that's 20. At this point, we're going to look at bond polarity using the Pauling electronegativity scale. And then we're going to look at 2 physical properties, specifically melting point and boiling point. And we're going to want to use the electronegativity difference between the atoms to explain why these physical properties vary, moving from each compound. And considering that the molecular weights are relatively in the same range. So in green, I'm going to write down some numbers, and these are the Pauling electronegativity numbers. So for methane, hydrogen's 2.2, carbon's 2.5. So the higher the number, the more electronegative, and based on that, we can draw a bond dipole, where starting at the lower number and pointing to the higher number, we put a plus, sort of like a cross-looking thing at the lower number. So that's one of the bond dipoles in methane. Considering that there are 4 equivalent CH bonds, all these dipoles would cancel out, and you would see that methane is a non-polar molecule. For ammonia, nitrogen has a value of 3.0. Again, hydrogen's 2.2. So the bond dipole would point that way. And again, keep in mind there are 3 equivalent NH bonds. All of those bond dipoles will sum together, giving a molecular dipole, resulting in a polar molecule. For oxygen, we have a value of 3.4, hydrogen's 2.2. Again, there's the OH bond dipole, so there'd be 2 equivalent bond dipoles for water, overall giving you a polar molecule. So in the periodic table, fluorine is the most electronegative element. It has a value of 4.0. Hydrogen's 2.2. So we end up with another polar molecule. So why is determining polarity important? Because that affects physical properties such as melting point, boiling point, and miscibility in water, so aqueous systems or organic systems. Let's look specifically at the melting and boiling points of each of these. So things melt first, we're going to record that in degrees C. They phase transition from solid to liquid, then they boil, again in degrees C, which they become a gas. So hydrogen has a melting point of negative 259, again in degrees C, a boiling point of negative 253. Methane is negative 183. It boils at negative 162. Ammonia melts at negative 77, and it boils at negative 33. Water melts at 0 degrees, boils at 100 degrees. HF melts at negative 84, and boils at 20. So if we examine the change that occurs, the very big jump that's observed in this region, we've already noted that methane is nonpolar, ammonia is polar. So there's one possible explanation as to why we see such a big jump in the difference of melting and boiling points, is the presence of polar bonds. Another thing that the nitrogen, oxygen, and fluorine can have that carbon cannot is called hydrogen bonding. So these elements, nitrogen, oxygen, fluorine, can hydrogen bond, and if you remember, that is an intermolecular attractive force. So these molecules are attracted to one another, so therefore that will effectively increase the boiling point along this trend. So to summarize, we've built molecules from the elements that are prevalent in organic chemistry 1, hydrogen, carbon, nitrogen, oxygen, fluorine. We've looked at the number of lone pairs each has and the number of sigma bonds each has in the normal valency state. We've written dashed formulas, condensed formulas, calculated molecular weights, which is important for mass spectrometry, and briefly looked at some physical properties based on bond polarity, which was determined from electronegativity.